Have you ever really truly stopped to think about what it means to see something? We all kind of assume our eyes are like little video cameras, just recording a perfect copy of the world. But the truth? It's way cooler and honestly a lot weirder than that. What you think of as sight isn't a recording, it's a full-on production, created and directed by your brain. And to really get how that works, we need to meet a man whose own experience blew up everything we thought we knew about seeing. So, get this. This is the true story of Dr. Oliver Sacks, a brilliant neurologist, a celebrated professor, a guy with a mind sharper than just about anyone. But he couldn't do something a baby can. He couldn't recognize his own reflection. How is that even possible? Well, that's the exact mystery we're going to unravel today.
All right, so here's our game plan. We'll kick things off with Dr. Sacks's curious case. Then, we'll break down the huge difference between sensing and perceiving. After that, we'll look at the surprising limits of our own senses, trace the incredible journey light takes to become a signal, and finally, see how the brain actually builds the world we see.
So let's talk about Dr. Sacks's condition. It's called prosopagnosia, which is a fancy term for face blindness. And here is the absolute key to this whole thing. There was nothing wrong with his eyes. His sensation was perfectly fine. The problem, the breakdown, was in his perception. It created this bizarre reality where he could easily spot his coffee mug on a crowded shelf, but he couldn't recognize his best friend walking towards him. To really wrap our heads around Dr. Sacks's world, we've got to get to the very core of how we all experience reality. See, it's not a one-step thing. It's a two-step process. And the gap between these two steps, well, that's where all the magic happens. So it all boils down to this: sensation versus perception. Sensation is the bottom-up part. It's just raw data. Your eyes, your ears, your skin, they're just collecting raw information from the world and sending it upstairs. But perception, that's the top-down process. That's your brain taking all that raw data and making sense of it, giving it meaning. So sensation is just light hitting your eye. Perception is your brain going, "Oh, hey, that's Mom."
Just think for a second about all the information hitting your senses right now. The hum of the lights, the feeling of your clothes, the air temperature. You're consciously aware of what? Maybe 1% of it? You can't hear a dog whistle. You can't see an ultraviolet like a bee can. Our senses are amazing, for sure, but they have very clear, very real limits.
Okay, so that first big limit is something called the absolute threshold. Now, the definition sounds a little technical, but the idea is simple. It's the absolute faintest thing you can detect. But here's the catch: only half the time. That 50% part is super important because it shows that our ability to notice something isn't a simple on-off switch.
So picture this. You're taking a hearing test. They're playing this incredibly faint beep. At a certain volume, you might hear it. Then the next time they play it at the exact same volume, you miss it. That tipping point, that 50-50 line where you catch it half the time, that's your absolute threshold for that sound.
So what makes you hear it one time and not the next? Well, it's all about context. It's not just about the strength of the signal, it's about your brain. Your alertness, your focus, your expectations, they all play a huge role. I mean, the classic example is the new parent, right? They can sleep right through a freight train roaring by the window, but the second their baby makes the tiniest whimper from the other room, boom, they're wide awake. Their brain is primed to listen for that one specific signal.
Now, what about noticing a change between two things? This is where another cool idea, Weber's law, comes in. And it basically says this: it's not the amount of change that we notice, it's the percentage of change. Think about it. If I hand you a 10-pound weight and then add one more pound, you'll feel that difference instantly. But if I hand you a 100-pound weight and add that same 1 pound, you probably won't notice a thing. It's all about the proportion. Okay, so let's follow the data trail. We're going to trace the path of light from the outside world all the way to it becoming the raw data of sensation. And we're going to focus on our MVP of the senses, our vision. Just how good is our vision? Check out this number: 1 million. That is roughly how many different shades of color the average person can tell apart. It's an absolutely incredible piece of biological tech, and it all starts with the simple journey of light.
And this whole journey happens in the blink of an eye. Literally, light comes in through the cornea and pupil. The lens focuses it, and it projects an image onto the back of your eye, on the retina. It's there that special cells translate that light into electrical signals, which then get zipped down the optic nerve straight to the brain.
Now, those special cells on the retina are a team of two. You've got rods and you've got cones. Think of rods as your night vision specialists. They handle black and white, they're great in low light, and they cover your peripheral vision. Cones, on the other hand, are the high-definition color artists. They're all clustered in the center of your vision. They give you all that amazing detail and color, but they need plenty of light to do their job. Okay, so we've tracked the sensation part. The raw data, the light, has been collected, translated into an electrical signal, and sent on its way. Now for the most amazing, most mysterious part of the whole process, perception. How does the brain take a stream of electrical pulses and turn it into, sight?
So those signals arrive at the visual cortex, way at the back of your brain. And here's what's so wild. The brain doesn't just look at one complete picture. Instead, it has these teams of feature detectors, tiny specialists that only care about one thing. One group only looks for vertical lines. Another only looks for movement from left to right. And it does it all at the same time, using parallel processing, to analyze color, motion, form, and depth simultaneously. It's unbelievably efficient.
So, if the brain processes all these features in different specialist areas, what happens if one of those specialists just isn't working? And this, right here, brings us back to Dr. Sachs and the answer to our mystery. His condition is tied to damage in one very specific spot, the fusiform gyrus. This is the brain's dedicated face-recognizing department.
And that is the final piece of the puzzle. His eyes were working fine. His sensation was perfect. They delivered the raw data of a face, the lines, the shapes, the colors, without a problem. But the specialized part of his brain that was supposed to take that data and perceive it, to assemble it into the concept of a face, that part wasn't working. He could see all the parts, but his mind couldn't put the picture together.
So this whole journey leaves us with a pretty mind-bending question, doesn't it? If everything you see is just your brain's unique interpretation of some raw data, what does the world actually look like? What's really out there, beyond what our brains are built to show us? It's a powerful reminder that the reality each of us experiences is deeply and truly our own.